Hello everyone, welcome back to Math with Allison. Today we are doing a Calculus 2 exam, so this is the second exam of the series. So let's go ahead and dive into it. In this exam, it was given spring of 2017. It is a real exam and it is currently given to students as study material for their upcoming exam. So this exam is going to be on different methods of integration, a little bit of sequences, and a little bit of series. So let's get started. They give us a very nice table. I don't think this is given to everyone. Look at cosecant cubed, secant cubed, like that is very nice. But let's try problem number 1. We want to find each integral. So part A here, we have the integral of 5x plus 2 times e to the negative 2x. Whenever you notice two functions of x being multiplied by one another, that is going to cue you into integration by parts. So here I'm going to set u equal to something, and I'm going to set dv equal to something. dv is something I want to be able to integrate. U is something I want to take the derivative of. So here I'm going to take the derivative of 5x plus 2, because when I take the derivative of it, I just get 5 dx. And so I get rid of an x term, right? My dv is going to be e to the negative 2x dx. And when I integrate both sides, we're going to get v is equal to negative 1/2 e to the negative 2x. So here, if you don't remember integration by parts, I remember as UV rays shooting at voodoo. So let's go ahead and fill that in. We get u, which is 5x plus 2, times negative 1/2 e to the negative 2x, minus the integral of v, that's going to be negative 1/2 e to the negative 2x, multiply that by our du, which is 5 dx. So here you can just leave that first term as is, right? Here I'm going to bring out all my scalar multiples, so that becomes a plus 5 over 2, and all that we're integrating is e to the negative 2x dx, which we know how to integrate that. That becomes plus 5 halves, and we're going to multiply that by negative 1/2 e to the negative 2x plus some constant c. If you wanted to take it one step further to simplify it, you totally could. And that right there would be your solution. So this is also totally correct if you don't want to simplify it. It doesn't say to simplify all of the antiderivatives. It just says find each integral, so up to you. Here we have tangent cubed of x times secant to the power of 4 of x. Think about derivatives. The derivative of tangent is going to be secant squared. And if I were going to use u substitution, I would want a secant squared in here. So here I'm going to rewrite this as tangent cubed of x times, and we can break this into secant squared times secant squared. The thing is that if I were to set u equal to tangent, I only want one secant squared. So let's go ahead and use its identity. Secant squared is equal to tangent squared of x plus 1. And then we multiply that by secant squared of x dx. So now I have most of our antiderivative is in terms of tangent, and I have our remaining secant squared of x dx. So this is very helpful. We can go ahead and set u equal to tangent of x, and we get our corresponding du is equal to secant squared of x dx. So let's go on and replace everything in our integral. Here we have, that's going to be u cubed times u squared plus 1 multiplied by du. So here you can simplify that inside. That's going to be u to the power of 5 plus u cubed du. Here we can take the antiderivative, so u to the power of 6 divided by 6 plus u to the power of 4 divided by 4 plus c. And our last step, of course, is to plug our u back in. So we get tangent to the power of 6 of x divided by 6 plus tangent to the power of 4 of x divided by 4 plus c. And that right there is our final solution. Another way you could have done this problem is you could have broken this up. So instead of doing tangent as our u, think about secant as our u. The derivative of secant is secant times tangent. So here we could have tangent squared of x times secant cubed of x, and then we have our derivative, secant x, tangent x. What you would do is you would replace tangent squared x with its identity, which is going to be secant squared x minus 1. And so right here, you would follow the exact same process. So u is going to be equal to now our secant of x. So then we get our corresponding du is equal to the secant of x tangent of x dx. So here you can replace everything back in, right? That's going to be the integral of u squared minus 1 times u cubed times du. And notice here, we're going to get something super similar. We get u to the power of 5 minus u to the power of 3 du. When we take the antiderivative, we get u to the 6 over 6 minus u to the 4th over 4 plus c, which this is going to be equal to secant to the power of 6 of x divided by 6 minus secant to the power of 4 of x divided by 4 plus c. And then these two solutions are both correct, right? They're equivalent, has to do with the identities, right? Okay, number 2, we're going to find each integral. So here we have the integral of x over x plus 7 over x squared plus 2x dx. So here I notice in the denominator that I can factor it. So we get x plus 7 divided by x, and that's going to be x plus 2 dx, which cues me into partial fraction decomposition. So here we have x plus 7 over x times x plus 2 is equal to some constant a over x plus some constant b over x plus 2. Now what we're doing is we're multiplying that by the entire denominator, x times x plus 2. So on the left side, we're just left with x plus 7, which is equal to a times x plus 2 because the x cancels out, plus b, and then that's just going to be x because the x plus 2 cancels. Here you can plug in zeros if you wanted to. So first you could plug in that x is equal to 0. On the left side, we get 0 plus 7 is just 7 is equal to, that's going to be 2a. And notice that this term zeroes out, which is the purpose of doing it. So we get 7 over 2 is equal to a. We can plug in our other 0, which is going to be negative 2. So here we get negative 2 plus 7 is equal to 5. And here our a cancels out or zeroes out, and we get negative 2 times b. And so if I divide by negative 2, negative 5 halves is equal to b. We can go ahead and replace that in our integral now. So this is equal to, and we get a over x, which is 7 halves over x. That's going to be minus 5 halves over x plus 2 dx. And this we can take the antiderivative of. We get 7 halves times the natural log of x minus 5 halves times the natural log of x plus 2 plus c. And that right there is our solution. Here we have the, look at this. We have an improper integral because we have a bound of infinity. It's improper because infinity is just a concept, it's not a number. So here, let's go and rewrite it first. The limit as b approaches infinity of 2 to b of 1 over x plus 1 cubed dx. So our first step is we want to find the antiderivative. So I'm actually going to rewrite it so we can see power rule really well. So I'm going to write that as x plus 1 to the negative 3 dx. So here, now we can go ahead and use power rule. I'm going to go ahead and add 1 to the power. So it's going to be x plus 1 to the negative 2. Divide by that new exponent evaluated between 2 and b. If you wanted to rewrite it, you totally could. So limit as b approaches infinity. That's going to be negative 1 over 2 times x plus 1 squared. And now we're going to go ahead and plug in upper minus lower. That becomes a plus because we're subtracting a negative. So let's go ahead and think about our b term. As our denominator gets really, really big, the entire fraction is going to approach 0, right? 1 divided or negative 1 divided by a really big number goes to 0. So here when we evaluate it, we get 0 plus 1 over 2 times 3 squared. That's going to be 1 over 2 times 9, which is equal to 1 over 18. And then that right there is our solution. Problem 3, we're going to use trigonometric substitution to find that integral right there. For full credit, leave no inverse trig functions in your solution. So you need to make everything in terms of x. So here, what cues me into which trig substitution I'm going to use is that this is going to be a squared minus x squared, which tells us we're going to use x is equal to a times sine of theta. So in this case, right, we have 9, which is equal to 3 squared minus x squared, which can be rewritten. So x is going to be 3 sine of theta. If you want to draw your triangle first, you totally could. This right here is theta. Pretend that's a perfect 90-degree angle. Here we have x divided by 3 is equal to sine theta, and that's helpful because it tells us our opposite, which is x, over hypotenuse. So our remaining leg is going to be the 9 minus x squared. So we have our x. We also need our dx, right, because we need to replace both in the equation. So let's go ahead and use this to find our dx. If I differentiate both sides, I get dx is equal to 3 cosine of theta times d theta. So now we have our x and we have our dx. Let's go ahead and replace everything in our integral. We get x cubed, so I'm just going to go ahead and cube it right away. So that's going to be 3 cubed, which is 27, sine cubed of theta. And then we're going to multiply that by the square root of 9 minus x squared. So that's going to be 3 squared 9 sine squared theta, all to the power of 3, times our dx, which is 3 cosine of theta d theta. We can go ahead and combine some things. So here, 3 times 27, that is going to be equal to 81, times the integral, that's sine cubed theta. That cosine of theta is right there. And let's go ahead and simplify the inside of this. So I can factor out a 9, and we get 1 minus sine squared of theta. And here, actually, we have 1 minus sine squared of theta. That is equal to cosine squared of theta. And here we can actually take the square root of both of these. The square root of 9 is just going to be 3. The square root of cosine squared is just going to be cosine. So what we get is 81 times, and that's going to be 3 cubed, which is 27. I'm not going to even multiply that because I don't know. I don't want to. You don't have to. Sine cubed, cosine theta, and then we get times cosine cubed theta, d theta. So we can combine those two cosines. That's going to be cosine to the power of 4. I know if I set u equal to sine, I need to have one extra cosine. But if I take one extra cosine of a cosine to the fourth, I'm going to have cosine cubed times cosine to the first. And cosine cubed, I'm not going to be able to use the trig identity. So I don't want to set it equal to sine. So what if I set u equal to cosine? Well, then I need one sine. So we have 81 times 27. Let's separate that into sine of theta times sine squared of theta times cosine of the fourth of theta d theta. With sine and cosine, the trick is split up whichever one is odd. Break one off, and then you'll be left over with an even one. The purpose of having an even power is so we can go ahead and replace it with a trig identity, which is going to be 1 minus cosine squared of theta. That way we have most of our integral is in terms of cosine, so we can set u equal to cosine theta. And here we have our corresponding portion for the du. So du is equal to negative sine of theta d theta. So let's go and replace everything. We're going to have that extra negative, so we have negative 81 times 27 times, we get 1 minus u squared times u to the power of 4 times du. So let's rewrite that inside the integral. We have that's equal to u to the power of 4 minus u to the power of 6 du. We can, of course, take that antiderivative. So here we're going to get u to the power of 5 divided by 5 minus u to the power of 7 divided by 7 plus some constant c. We need to replace what our u is equal to, which is going to be cosine. Cosine to the power of 5 of theta divided by 5 minus cosine to the power of 7 of theta divided by 7 plus c. We need to finish in terms of x, which is why we drew this triangle up right here. Cosine of theta is going to be adjacent, which is the square root of 9 minus x squared divided by the hypotenuse, which is 3. So let's go ahead and replace that in here. I scooted over so I had room to write it. So this is equal to negative 81 times 27, yada, yada. So that's going to be 1/5, right? We have a scalar multiple. We have the square root of 9 minus x squared divided by 3 to the power of 5 minus 1/7, scoot it over more. The square root of 9 minus x squared divided by 3 to the power of 7. Oh, plus c. This thing right here, oh my gosh, so big. That right there is our final solution. Ooh, okay, we're getting into series. So what does a divergence test tell you about each of these series? With a divergence test, you take the limit as whatever your index is, so in this case it's k, approaches infinity of our little formula in here. So natural log of k divided by k. So here, notice this approaches infinity over infinity, which tells us we can go ahead and use L'Hopital's rule. So using L'Hopital's rule, we get limit as k approaches infinity. Derivative of natural log k is 1 over k, which we get over 1. So that's just equal to the limit as k approaches infinity of 1 over k, which we know is going to approach 0. Since this equals 0, the test is inconclusive. It doesn't tell us any information. Let's go and try this other one. We're going to take the limit as k approaches infinity of 1 minus k cubed divided by 1 plus 1,000 k cubed. So since this is a limit at infinity, you can just take the highest powers with their coefficients. So here this is equal to the limit as k approaches infinity of negative k cubed divided by 1,000 k cubed, which we can go ahead and simplify that, right? That's just going to be negative 1 over 1,000. And the limit of a constant is just equal to that constant, so negative 1 over 1,000. This is not equal to 0. That tells us that the series is going to diverge. Part B, we're going to evaluate this series or explain how you know it's divergent. So when I look at this, I have a power n, I have a power of n plus 1. What this looks like to me is a geometric series, but we need to go ahead and manipulate it. The first thing we need is for it to start at 0. So I have a summation n equals 0 to infinity. Since I subtracted 1 from the index, everywhere I see an n, I'm going to add 1, so 3n plus 2. So let's go ahead and use properties of exponents to rewrite this. So that's going to be 2 to the n times 2 divided by 3 to the n times 3 squared. Let's go ahead and separate this into just coefficients and then those powers of n's. So here I got that 2 divided by 3 squared, which is 9. And then with the powers of n's, I have 2 to the n divided by 3 to the n, which I can combine into one fraction. That's going to be 2 over 3 to the n. And here we have a geometric sequence where we can see r is equal to 2/3. And since r is less than 1, this series will converge. We can find what it converges to using a over 1 minus r. So let's go and replace this. So that's going to be our first term, which is 2/9 divided by 1 minus 2/3. That is equal to 2/9 divided by 1/3, which we can rewrite as 2/9 times 3 over 1. Those cancel out, so we're just left with 2/3. So ironically, it also converges to 2/3. We're going to follow a similar process for this next series. It already starts at 0, which is very nice. But here we have 3, and we can write that as 10 over n. So here we can see our common ratio is going to be 10 divided by 9. And since we have the common ratio is greater than 1, that's going to tell us that the series will diverge. Now we have a sequence. Here we have the sequence, so n over n plus 1, evaluated from, that should be like n equals 1 to infinity. First, we're going to list in order the first 5 sequences of the given term. So first we have n is equal to 1. We get 1 over 1 plus 1, which is 2. N is equal to 2, we get 2/3. N is equal to 3, we get 3/4. N is equal to 4, we get 4/5. And n is equal to 5, we get 5/6. And then it'll go on forever. Does the limit of the sequence exist? Let's go ahead and try it out. We have the limit as n approaches infinity of n over n plus 1. If you want to think about it in terms of L'Hopital's, we have this is going to approach infinity over infinity, which tells us we can use L'Hopital's. So we have the limit as n approaches infinity of 1 over 1, which the limit of a constant is just going to be equal to that constant. So it does exist. We found its value. It's equal to 1. Okay, we're going to answer yes and no to the questions. I'm going to rewrite our sequence. So is the given sequence increasing? For it to be increasing, every term has to be strictly less than the following term, which you can see that all of these terms are going to be strictly less than the next term. So we have this is going to be yes. Is it decreasing? Well, it's increasing, so no. But to be decreasing, we have a sub n is strictly bigger than each following term. Is it non-increasing? When we're working with non-increasing, that means that we have that each term is going to be greater than or equal to the next term. In this case, it's going to be no, right? But it will be non-decreasing. We have that each term is going to be less than or equal to the next term. So that's going to be a good yes. Is it monotonic? Well, it's non-decreasing, so yes. If it's non-decreasing or non-increasing, then it's going to be monotonic, right? And then is it bounded? Well, we found its limit. Yes, it's bounded. It's going to be limited by 1, which makes sense because these numbers, the next one's going to be 6 over 7, 7 over 8, 8 over 9, 9 over 10, and notice how these are getting closer and closer to 1. Okay, and then here we got some multiple choice. So we are going to you just have to circle the correct answer. Which substitution should be used to find this whole integral? So in order to look for trig substitution, I want to see my a squared and my x squared. That's going to be a squared plus x squared, which cues you into x is equal to a tangent of theta. And that is going to be 2 right here. That's a squared is going to be 5 squared plus x squared. And so that tells us a is equal to 5. Next, we got which substitution should we use? So here I can see where my substitution is going to be. So when we have x squared minus a squared, we're going to go ahead and use x is equal to a secant of theta. A in this case is going to be 10. So here we get 3. Which expression gives the correct way to evaluate that integral right here? This is an improper integral because we have one of our illegal values in our domain. So we want to go ahead and replace our upper domain. So I see this one, the bottom's replaced. For 2, the bottom's replaced. So I know I don't want either of those. So let's go and look at 3 and 4. Both of them are going to replace that upper bound of 8. But are we approaching 8 from the right or the left? Well, just think about the interval we're on. We're going from 0 all the way to 8, which means we're approaching 8 from the left side. And so that's going to tell us 4 is the correct answer. See which one statement is true about the sequence. It converges to 0, it converges to 1, it converges to 2, or it does not converge. Well, let's go ahead. We can use the limit as n approaches infinity of, that's going to be 2 plus negative 1 to the n divided by n. So even though that this right here is the negative 1 to the n, it's going to be oscillating between positive, negative, positive, negative. But that denominator is going to get really, really big. So really, this whole thing is going to approach 0. So this is equal to 2 plus 0, which is equal to 2. So it's going to go ahead and converge to 2. You could also use a squeeze theorem. So this is going to be bounded between 2 minus 1 over n and 2 plus 1 over n. Both of those, when we take the limit, as n is going to approach affinity, are going to, both of those are approaching 2. So it's bounded between 2 and 2. It tells us it equals 2. Okay, part E. Suppose the sequence a sub n is defined by the recurrence relation a sub n plus 1 is equal to 1 minus 1 over a sub n, and they give us the first term, a sub 1 is equal to 2. What are the first 4 terms of the sequence? So let's go ahead and find our a sub 2. That's going to be 1 minus 1 over a sub 1. That's going to be 1 minus 1 half, which is equal to 1 half. So our second term is going to be 1 half, and that already cancels out 3. Our A3 is going to be 1 minus 1 over A2. That's going to be 1 minus 1 over 1 half. That's equal to 1 minus 2, which is negative 1. So our next term should be negative 1, and the only option there is going to be 2. If you wanted to check your work, you could find a sub 4. So in this case, we get 1 minus 1 over negative 1. That's going to be 1 plus 1, which is equal to 2. And that right there is our fourth term. So check your work. And that is the end of the exam. So exciting. So that's all I have for us in this video today. If you enjoyed it, I have many more like it. So make sure to check out my playlist that's linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.